this image for a couple of reasons. First, if I only gave you the options of saying that the cup is either half full or half empty, I hope you would select that the cup is half full. I think your life will go a lot easier if you're a half full person. However, I'm also showing you this image because I want you to think of this cup as being completely full, the bottom of the cup being full of water and the top of the cup being full of air. Because what we're going to be talking about is sound waves, and if you don't appreciate the fact that the air around us is, or I guess I should say the space around us is completely filled with air molecules, then it gets more difficult to appreciate how sound waves work and how wonderful it is that I'm able to communicate things to you because of the fact that we have an atmosphere which allows sound waves to be traveling through the space between us. The picture that we're going to use to understand sound waves is a slinky moving back and forth, where we're moving our hand forward and backward along the direction of the slinky, which creates a longitudinal wave. And we know that as I move my hand back and forth, it's going to create compressions and expansions of the coils in that slinky. And the same thing happens when I create a sound wave. So for example, if I take a tuning fork and I hit the tuning fork with something, then the tines, the prongs of that tuning fork oscillate back and forth. And as they oscillate back and forth, they also create compressions and expansions. But this time, instead of it being the coils of the slinky, it's the air molecules. There are regions of high pressure and regions of low pressure that are created by the back and forth movement of the tines of the tuning fork. And another important thing about this is that the slinky is confined to, the one dimension of the slinky, but when I create sound waves, this happens in 3 dimensions. They go out in every direction. And so to summarize, sound waves, like the waves produced on a slinky when you move your hand back and forth, are longitudinal waves. And the compressions and rarefactions of the air molecules are due to vibrations. So I can speak, or I can hit a tuning fork, or I can slap my hand down on my desk, and any of those things cause vibrations, which cause sound waves. This is a wonderful GIF that shows in real time what a sound wave would look like if we were able to see all of the air molecules. And first, I'd like you to appreciate this on a macro scale and just say, I definitely see a wave traveling to the right. You can see all of the black molecules, and it looks like there's a net movement of particles moving to the right. But if you look at any of those red particles that have been highlighted, you can see for sure that all of those particles are only moving back and forth, oscillating like the coils of a slinky, not moving really anywhere. There's no net movement. They just kind of go back and forth in place. And it's not an optical illusion. Even if you pick any of the other black molecules, you can see that they too are just moving back and forth. So the molecules don't move from place to place. The energy or the disturbance, the wave, moves from point A to point B, not any of the individual particles themselves. And of course you can see the compressions, the rarefactions, the places where there's high density and low density. So again, the individual particles of air are moving back and forth like the coils of a slinky. And if I were to make a graph of the density as a function of position, I would get something that looked like a transverse wave. So even though this is a longitudinal wave, depending on what I graph, I can graph something that looks like a transverse wave, and so the density as a function of time looks very wave-like, right? Where there are regions of normal density, there are regions of high density and low density as I move across the wave. The speed of sound, which I have very largely here, is 343 meters per second. And that is a very specific number. And you might ask, is the speed of sound a constant? And I respond to that by saying kind of, because for all practical purposes, at normal conditions, the speed of sound will be about 343 meters per second. But there are things that affect the speed of sound. What the sound waves are traveling through is important, the temperature is important, and the density is important. So the 343 meters per second is the speed of sound in air at normal temperature and density conditions. And so if I'm traveling through something that isn't air, it could be much slower or faster. If the temperature goes up by a lot or down by a lot, or the density goes up or down by a lot, then the speed of sound can be affected by that. For example, most of the time we listen to fireworks, not listen, we view fireworks, but we also listen to them while we're viewing the fireworks in July, right? Or at least sometime during the summer where it's very hot, maybe it's 80 degrees. And at Valparaiso University, they do a uh, a celebration around Christmas time where they light a Christmas tree, and then after they light the Christmas tree, there is a huge firework display. And sometimes it's quite cold around Christmas time, right? And it's about 0 degrees on some of the years where I attended this. And they light the Christmas tree and the fireworks go off. And the difference in temperature from when I normally listen to fireworks in July to when I was listening to fireworks at some of these firework displays in December was maybe about 80 degrees. And so that creates quite a significant difference in the speed of sound. And so I can't say for certain whether or not that's the only thing that I was, observing, but I do think I noticed a difference in how I was hearing the fireworks in December versus July. This is a table that has a bunch of different materials and the speed of sound in those materials. And so you can see air at about 20 degrees Celsius near the bottom, 343 meters per second. And you can see a lot of interesting things here, like for metals like aluminum or steel, the speed of sound is incredibly fast. And so you should ask yourself questions like, why is the speed of sound so fast in those materials? Well, those materials are much more dense. The molecules are so much closer to one another, and so it's easier to communicate the disturbance of that wave when the molecules are closer together. Also, one interesting thing to point out is helium is on this list near the bottom. In helium, sound travels, 2 or 3 times faster than what it does in air, and so that maybe that makes sense as to why when you inhale helium and speak after inhaling some helium that your voice is so much higher. You should be able to work out why that's happening. The speed of sound is pretty fast. 343 meters per second is pretty fast, but it does not compare at all to the speed of light. The speed of light is about 300 million meters per second, so not even close. Planes can travel at a wide range of speeds, but a lot of them travel at about 240 meters per second. Of course, we maybe have seen videos of jets that are traveling faster than the speed of sound. They break the sound barrier and you hear that loud sonic boom. But most planes travel well below the speed of sound. Bullets also travel at a wide range of speeds, but there are some that travel much faster than the speed of sound. And so for that reason, when you are playing a video game or watching a movie, it should be the case that for most guns, you would be hit by the bullet or see somebody hit by the bullet before they heard the sound. In some games, in some movies, they get that right, but then in other cases, they don't. And so it's just an interesting thing to look for. The last thing I'd like to do for this first set is work out a problem which incorporates the fact that I know the speed of sound in certain conditions is going to be a constant value of 343 meters per second. Here's a problem where I'm going to drop a stone from rest into a well, and the water is 7.35 meters below the surface where I'm dropping the rock. And I'd like to know how much time it takes for me to hear the splash. And so the first thing I'm going to recognize is that I can use kinematics to figure out how much time it's going to take for the stone to hit the water in the well. And so I work this out and I say the initial velocity is 0, so the first term in my equation goes away. It's 0 because I'm dropping the stone from rest. I can now solve for t because I know that the water is 7.35 meters below the surface, and I know what g is. And so when I solve for that time, I get TD, I'm writing TD here because it's the time for the drop, of about 1.22 seconds. But how much time it takes for me to hear the splash is not equal to 1.22 seconds. It's close, but not quite, because after the rock hits the water, it then will take time for the sound wave to travel up the length of the well. And so 1.22 seconds is the time it takes for the stone to drop that 7.35 meters, but I'm not quite done yet. In order to find the time it takes for the sound to come back up, that sound wave is not affected by gravity. It's just distance divided by time. Those sound waves are traveling at a constant speed. And so the distance the sound wave needs to travel is back up the well, which is 7.35 meters, and the speed that is traveling at will be 343 meters per second, given we're working in air and in normal conditions. And so the time for that returning sound wave to come back up, TS, is 0.02 about. And so if I wanted to know the time that it takes for me to hear the splash, that's the time for the drop plus the time for the returning sound wave. And so I need to add those two things together. And when I do that, I get a time of about 1.24 seconds. So the returning sound wave is a very small fraction of that amount of time. But if you were designing an experiment where you needed to listen for something, then it would be important to incorporate the distance that the sound wave needs to travel in order to be making sure that you're measuring the correct times.